Hello. In this video, we are going to solve a simple air standard Brayton cycle problem. The Brayton cycle shown in this schematic here has been transcribed into this TS diagram. 1 to 2, the isentropic compressor, this is an ideal Brayton cycle, is shown here. 2 to 3 is where the heat addition takes place, Q dot in, and 3 to 4 is where the turbine produces work, and the net work is, some of it is supplied to the compressor, and 4 to 1 is the heat rejection, Q dot out. So the states are given. State 1 is given to us, and instead of mass flow rate, the volume flow rate is supplied. The pressure ratio of the compressor is given, and the maximum temperature, 1100 degrees Celsius at state 3 is given to us. So with that, let's first evaluate all the anchor states, 1, 2, 3, 4, analyze each device, and then let's see how the test step puts all of it together to find all the cycle variables. Brayton cycle is discussed in chapter 8 in your textbook. So I've already logged in as a student at thermofluids.net. So to start the app, we go to test app, follow the open system specific branch, and vapor power and gas powers are all bunched together here. And gas power depends on what model you pick. In this case, we are asked to use the PG model and do a what if study using the IG model. So let's go launch the test app. And I'm assuming you're familiar with device analysis, which is covered under single flow devices in the open branch. So to move quickly, we'll find the anchor states. State 1 is our inlet state. Air is already the designated working fluid. 100 kPa and 25 degrees Celsius. Volume flow rate is 8 meter cube. And that completes the state. For state 2, instead of entering the pressure directly, we'll declare the pressure ratio here as R equals 12, pressure ratio of 12, yes. In here, calculate. So it has been registered. We go back. For state 2, we'll write equals P1 star R instead of 12. The reason is that then we can change R later on in the I/O panel, and we can very quickly figure out its effect on the entire cycle. Of course, the mass flow rate and entropies are same as state 1, m dot 1. And for state 3, we'll spawn the state using plus instead of starting from scratch. That way, state 3 is a copy of state 2 now, but we know P3 will be equals P2. Mass flow rate is the same. And for state 3, temperature is equals, that's the maximum temperature of the cycle. Wait, but we haven't declared what is Tmax, so you go back, the white background indicates that. We go back to the I/O panel and declare Tmax to be equals the maximum temperature, which is, I believe, 1100 degree Celsius, which is so many Kelvin. Once it's declared and calculated in the I/O panel, if you come back in the state panel, do a calculate again. Now Tmax is registered. If you put your pointer over Tmax, you can see its value will appear right in this spot, 1373 Kelvin. So state 3 is done. So for state 4, we're back to pressure 1. Isentropically, it's the turbine. And of course, I could have spawned the state, then I didn't have to type that in. So all the 4 states are done. Let's go to the graphics panel to make a quick check. Yes, it looks logical. And now we go to the device panel to do the analysis of each device. Here is our compressor, state or operating between state 1 and 2 requires this much amount of external work, which is negative because work is going into the compressor. Then we have constant pressure heating between state 2 and state 3, and there is no work there. This is the amount of heat that is added, that's Q dot in the cycle. And between 3 and 4, we have an isentropic turbine, which is adiabatic. So this is the work output of the turbine. And finally, between 4 and 1, we have constant pressure heat rejection. Heat is rejected, that's why it's negative. So all the 4 devices have been analyzed, and the cycle panel is ready for us. As you can see, all the answers we are looking for. What is the net work? So many kilowatt. What is the back work ratio? So many percent. What is the thermal efficiency? 50.86%. So let's write down some of them, some of this number, so that we want to see a what-if study, different kind of what-if studies. For instance, suppose we want to know how will the the pressure ratio affects the efficiency. Suppose from 12 we change it to 15 and hit calculate here to update the pressure ratio. We super calculate. All our answers are updated, and you can see the results. You can go back to the cycle panel. The efficiency become 53.9%. So efficiency increased by almost 4% or so. The network, we can see also 3672, barely changed. 3657 was the earlier value. Anyways, so you get the idea how to conduct a parametric study. Going back to the original value, 12, let's reproduce the result, calculate, super calculate. So we should get back our original efficiency, 50.86%. So how do we now repeat this calculation for the IG model? Well, the super calculate will always produce the test code. We copy Control A, Control C, test code. Go back to the, we go to another, we launch another version of the test steps on a new tab. Go to IG model to launch the same test step with the IG model. And now all we do is to go to the IO panel, paste the test code, and click the load button. Voila. So it's done. Now you can go to the cycle panel and compare what happened to the efficiency. It decreased slightly from 50% to 48%. This was our PG model result, if you recall. And these are our IG model results. What is IG model? CP and CV are variables, function of temperature. And PG model simplifies it by assuming CP and CV are constants. So anyways, so you can see the effect of changing the model on the all kind of analysis of gas turbine. You name it. Output 33960 is slightly higher. Similarly, efficiency on the other hand is slightly lower because CP is a variable now. And as you can see in the IO panel, you can go in the user code, change Tmax for instance, and see how it impacts cycle variable. I'll stop here. I verified the manual results, and you can use these test codes to pursue whatever interests you.